Viewers like you make this program possible. Support your local PBS station.
Most people sense a change in the weather. It's not your imagination.
Megastorms, droughts, fires.
We're seeing 1 in 1,000-year floods with astonishing frequency.
How many times does that have to happen before it's not a fluke, but it's a trend?
Is this trend the new normal?
Our planet did not come with a manual of how it all works.
To understand how it works, NOVA explores one of the greatest scientific quests of all time.
This is the essence of science.
A global investigation of our climate machine.
Looks good back there.
And how it determines our weather.
Yeah, super clean data. The technology is a huge leap forward. It's game-changing.
It's just been like flipping on the lights.
It is a historic adventure.
The science goes back almost 200 years.
It was one of these things waiting to be discovered.
Probing deep into our natural world.
There's really nothing like it in science.
Looking for clues from Greenland's ice sheet.
The only way out of there is that helicopter. You're certainly not walking out.
To the desert of Australia.
It gives us a really important window into the past.
The stakes are high, yet the outcome uncertain.
We're poking at the climate system with a long, sharp, carbon-tipped spear.
And we cannot perfectly predict all of the consequences.
Can these discoveries show us where our planet is headed?
What gives me hope is that we understand this, so we actually can do something about it.
It's a planetary crisis, but we're clever enough to think our way out of this.
Right now on NOVA, Decoding the Weather Machine. At a weather studio in Minneapolis, Minnesota, there is a storm brewing.
The models aren't sure where this thing is going.
And TV meteorologist Paul Douglas is trying to predict its path.
There's the eye, so it's moving more northwest.
It's still a very strong tropical storm.
I don't think anybody in their right mind sets out to be a meteorologist. Meteorologist Paul Douglas with an update on Irma. I'm going to be wrong frequently, and people will second-guess me, and I will get verbal abuse. And of course, the big story, Marco, the damage quite extensive. Predicting the future, 140 miles an hour, it's not for the faint of heart.
Because the weather these days is not for the faint of heart either.
All the ingredients converging to turn this into a true superstorm.
While Paul is reporting on a Category 5 hurricane threatening the U.S.,
Once again, smoke dominates.
his team is also reporting on wildfires in the West.
We've got a multitude of active large fires.
As we head into the upcoming...
And another megastorm en route.
It could be making a very close call with the Bahamas. We'll keep you up to date.
It's an atmospheric free-for-all.
Now, the Twin Cities' fastest-growing television news.
Over nearly 4 decades of blizzards, hurricanes, and floods, Paul has seen it all.
It may have been the most extreme outbreak of heat and humidity on record. The grips of the worst blizzard of the century.
But over the years, storm by storm, Paul began to develop an uneasy feeling. He wondered, was something up with the weather?
The rhythm of the atmosphere was off. We were seeing more freakish weather. Storms were stronger and wetter. It wasn't the old-fashioned minus 20, minus 30 winters anymore. It was raining in January. How many times does that have to happen before it's not a fluke, but it's a trend?
Paul had heard about global warming. But given all the crazy weather he'd experienced, he was skeptical. And he's not alone. 1/3 of Americans doubt humans are changing the climate.
We pray that you would awaken us.
Paul understands where they're coming from. many in his community of Christian conservatives are distrustful of big government.
A lot of the pushback is because when people look at climate change, they think, oh my God, if this is true, the only possible solution is more government, more regulation, EPA times 100.
But dealing with the weather day in and day out forced Paul to confront a question we all ultimately face. Is the frequency of powerful storms and odd weather patterns just normal weather variability?
Why has this gotten so big and so ferocious?
Or is it a new normal?
They've shut down almost 30 roads.
Most people sense a change in the weather. The weather's out of tune.
So how can we decode these changes? Paul is not the only one noticing changes. 7 of the 10 hottest years on record have occurred within the last decade. Wildfires are at an all-time high, while Arctic sea ice is rapidly diminishing.
We are seeing 1 in 1,000-year floods with astonishing frequency.
When it rains really hard, it's harder than ever.
We're seeing glaciers melting, sea level rising.
The length and the intensity of heat waves has gone up dramatically.
Plants and trees are flowering earlier in the year. Birds are moving poleward.
We're seeing more intense storms.
Changes like these have led an overwhelming majority of climate scientists to an alarming conclusion. It isn't just the weather that's changing, it's what drives the weather. Earth's climate.
Climate change is happening now, and the damage is happening now.
People notice extremes, and climate change is increasing the risk or probability of certain types of extreme weather events.
If we look all around us, we see over 26,500 independent lines of evidence that the planet is warming.
But while there may be evidence for a changing climate, hasn't Earth's climate always been changing? Glacier expert David Holland says the evidence for that is as solid as rock. Walking through Central Park in New York City, he finds a huge boulder, impossibly balanced on bedrock.
It's a different type of rock than any rock that we can see in the neighborhood. This rock was clearly transported here by some mechanism.
And the mechanism powerful enough to carry this huge boulder was a glacier. A vast sheet of ice.
Unquestionably, there was a very large glacier over Manhattan almost 20,000 years ago.
20,000 years ago, New York City looked very different from today. It was a much colder place, covered by ice that extended down from the North Pole.
And very carefully.
Open the pages
Oh,
of the book.
yeah, look at that.
And there is evidence that millions of years before that, the Arctic was completely different too. Fossils have been found of palm trees in a place now famous for ice and snow, Alaska. Earth's history is full of dramatic swings from hot to cold. So isn't today's changing climate just natural? The scientific evidence says no, and points to a very different cause. Us, primarily through our burning of fossil fuels. That's a serious charge, and addressing it will be enormously expensive. So what is that evidence? The quest to understand what is behind our changing climate began, surprisingly, more than 200 years ago.
At the end of the 18th century, there's really this flowering of fundamental exploration of science of all kinds.
Andrea Sella, a chemist at University College London, says scientists at the time were out exploring the natural world and what factors control Earth's climate.
One of the things that's very interesting at the time is this idea of what heat actually is. People are beginning to realize that there are these invisible radiations that can convey heat. Today, we call it infrared radiation. It's what you feel when you're standing in front of a roaring fire, but it's invisible to our eyes.
A Frenchman named Joseph Fourier, science advisor to Napoleon Bonaparte, wanted to understand if these invisible radiations of heat helped determine Earth's temperature. He reasoned that if sunlight just warmed Earth, the heat should build up and the planet would be intolerably hot. But if all the heat coming in radiated right back out to space, our planet would be cold.
Fourier sets up the first kind of scheme for understanding that balance between energy in and energy going out.
Fourier was intrigued by a simple experiment with a dark box, a thermometer, and a pane of glass that could explain how Earth's temperature was set.
The really striking thing is that when he turns it towards the sun, the temperature of the thermometer goes up and up and up. If he takes the thermometer out, the air is very cool, but when he puts it back in, the temperature rises again.
Why does the air inside the box heat up? The glass must be allowing heat from sunlight into the box and trapping some of it. Fourier wondered if something similar in the atmosphere was doing the same thing as that pane of glass, helping to regulate Earth's thermostat. While not exactly how our planet works, this metaphor was a first step in figuring out our climate. Earth's climate is set by a complex interaction among its four major components: land, sea, ice, and the atmosphere, or air. Fourier had zeroed in on the role of air.
In 1824, Fourier was the first to deduce that it's the composition of the atmosphere that governs the surface temperature of the Earth. 1824, almost 200 years ago. And climate science has been accumulating ever since.
He plants a seed, this idea that the atmosphere is trapping some of the heat that comes down from the sun. And the real question is, how does that happen?
40 years later, John Tyndall, another prominent scientist, discovered a clue about how Earth's atmosphere is heated with an experiment at London's famous Royal Institution.
The Royal Institution was a place which combined cutting-edge science and the equivalent of TED Talks of today. Public lectures in which the latest science could be communicated to the common man.
Tyndall wanted to figure out if a gas in the atmosphere was trapping heat like that pane of glass. After making a breakthrough in his lab, Tyndall quickly went public with a dramatic live presentation.
He presents it to the public. You know, here is the latest science, and he is redoing the experiment step by step and explaining his thought process.
Tyndall's original lab equipment is still housed at the Royal Institution, and Sella has dusted it off to bring this famous experiment back to life.
This is the business end of the whole experiment. It's what's called a thermopile, and it was something that had only recently been invented.
Two sensors inside measure heat.
If there's a difference in temperature between one side and the other, what it does is it produces a little voltage and an electrical current that's going to flow down these wires. And then you can measure it using a voltmeter.
Tyndall's idea was to use this sensor to measure the temperature difference between two sources of heat. On one side was a tube that he could fill with different gases.
What he does is he lets in a gas into the tube. He starts with air, then he moves on to nitrogen, to oxygen, essentially to every gas he can think of.
To Tyndall's surprise, when he tested the two gases that make up 99% of the atmosphere, nitrogen and oxygen, the needle on the voltmeter didn't budge. Those gases had no effect on the heat. Tyndall then tested a gas that exists in only trace amounts in the atmosphere, carbon dioxide.
And when he does carbon dioxide, he realizes that the radiant heat from that end doesn't make it through to the thermopile. In other words, what he's got his hands on a substance which will trap heat in the sky.
Tyndall had solved the mystery posed by Fourier's glass box. It was carbon dioxide and a few other trace gases like water vapor that trap heat radiating off the planet. These gases, called greenhouse gases, exist naturally. Sunlight passes through them and warms our planet. That heat radiates back out as infrared light. But some of the heat gets trapped by the greenhouse gases, and they help warm Earth like a blanket. At the time of Tyndall's discovery, England was being transformed by an industrial revolution that has changed the way we work and live. That revolution was powered by burning coal and oil.
Tyndall figured out that carbon dioxide traps heat. But even more importantly, Tyndall realized that when we dig up coal and burn it, it's actually releasing more of these heat-trapping gases.
Coal and oil are formed mainly from small plants and algae and are mostly made of carbon. After being buried for millions of years, when that coal or oil is burned, the carbon reacts with oxygen to form carbon dioxide. That is released back to the atmosphere, adding more greenhouse gases. These gases, in turn, act like an extra blanket, trapping more heat. But how much of this heat-trapping gas is there? And what impact does it have? To figure that out, climate research would need to be taken to new heights. Literally. Ralph Keeling of the Scripps Institution in San Diego has come to Hawaii to see just how much carbon dioxide is in the air, and if that amount is changing. Perched on a volcano, the National Oceanic and Atmospheric Administration's Mauna Loa Observatory is one of the most important atmospheric research sites in the world.
It's almost like a pole 2 miles high sticking up from the middle of the ocean.
So we're above this cloud layer, and for sampling carbon dioxide and getting numbers that are representative of a really big picture, it's nice to be away from the surface, so you're away from all these local influences that might change the carbon dioxide levels.
Samples are continually drawn from the air and analyzed, which can reveal clues about the health and functioning of our planet.
We're basically measuring a vital sign of the Earth by probing deep into the core of the atmosphere.
This atmospheric measurement was pioneered by Ralph's father, Dave Keeling, in the 1950s. His great innovation was to figure out a way to accurately measure the amount of carbon dioxide in the air.
He developed an apparatus that allowed him to do more precise measurements than had ever been done before.
But could such an extremely sensitive measurement be taken in this remote location, serviced by one unpaved road?
It was a remote site. A lot could go wrong. So it was a pretty nervous time as to whether things were really functioning.
At first, everything ran smoothly, and the measurements were exactly as he expected. But then, something happened.
The generator on the station failed, and the next time the generator came on, the measurement was drifting downwards. And he was thinking, oh no, something erratic with the instrumentation. We don't really know how this is working. Then there was another power outage, and it started at an even lower level, now it was drifting upwards. It looked problematic, to say the least.
Ralph's father, Dave, didn't know what to make of these erratic results, but he kept going. Several months later, the measurements started going down again. Suddenly, the answer dawned on him. Instead of a bad measurement, it was a whole new discovery.
By the beginning of the next year, you realize, oh, this is just the seasons. I'm seeing the seasons. It's real. It's not a bad instrument.
Dave Keeling's instruments were working perfectly, so much so that they had detected a subtle interaction between plants and the atmosphere. Trees breathe in carbon dioxide, drawing it out of the atmosphere, and use the carbon to grow leaves in the spring. In the fall, when the leaves die and decompose, some of that carbon goes back into the atmosphere. This annual rise and fall of carbon dioxide is what Dave Keeling discovered. It is the breath of the world's forests.
It never occurred to him that he would see this. It was one of these things that was just waiting to be discovered.
That breath can be seen today with images created from NASA's satellite data. These clouds are carbon dioxide moving through the atmosphere. Red shows the highest concentrations. Over the northern hemisphere, you can see the forests absorb carbon dioxide in the spring and summer and release it in the fall. The breadth of the forests explains the zigzags in the Keeling curve. But the measurements also reveal something alarming. The zigzagging curve was increasing each year.
You see the wiggles already up and down in the first few years. And if you look at it over this now almost 60-year time frame, you see that it's accelerating upwards.
The Keeling curve established without question that the carbon dioxide content of the atmosphere was going up steeply, sharply, rapidly.
But how unusual is this rapid rise? Keeling's measurements go back 60 years. But that's still only a tiny window on Earth's vast climate history. To put that rise in perspective, we would need a time capsule deep into Earth's past. Fortunately, there is one. Only it's buried in one of the most inaccessible places on Earth, the interior of Antarctica.
The interior is like being at sea. It's just this immense mass of ice. It's just really an astonishing thing to see.
But geologist Ed Brooke of Oregon State University doesn't come here for the scenery. He and other polar scientists are on the hunt for ancient air, captured in ice. These expeditions can last years and reach deep below the surface.
The ice drill can drill down into the ice sheet break off a core and bring it back to the surface. We take out ice yard by yard, and the deepest ice cores are over 2 miles deep.
Snowfall builds up in layers each year and is compressed to form huge ice sheets. So drilling down 2 miles can reach back to snow that fell a very long time ago.
And in those layers, there are gas bubbles that are trapped. And we can now analyze the composition of those gas bubbles and understand what the carbon dioxide content of the atmosphere was 100 years ago, 1,000 years ago. In the Antarctic ice sheet, we can go back 800,000 years.
Back in Ed's freezer, samples of ice are selected and prepared for analysis. Clearly visible within them are tiny, precious bubbles of ancient air.
I never get tired of looking at the bubbles. It's remarkable that we have this old atmosphere in our freezers.
Crushing or melting the ice releases the air.
There's really nothing like it in science. Normally we have to make kind of indirect inferences about the past. But in this case, we have these tiny capsules of air that we can directly measure.
When Ed measures the recent levels of carbon dioxide in the samples, it confirms Keeling's data. Over the last 60 years, the trend is the same.
The ice core record connects directly with the Keeling curve, which is one of the reasons we know the ice core record is so good, because the data show the same thing.
But these ice cores can extend the Keeling curve back in time and reveal that today's concentration of carbon dioxide is unusually high.
The current concentration of carbon dioxide in the atmosphere is higher than it has been for 800,000 years.
But it also shows something else, an overall pattern with levels of carbon dioxide rising and falling.
The pattern repeats itself. There are small variations. Each cycle is a little bit different, but they're not random looking at all. They're actually quite regular.
This regular pattern raises an important question. What does it have to do with climate? One way to get at that is to compare carbon dioxide levels with past temperature. Andrea Dutton of the University of Florida is looking for clues about Earth's past temperatures in seashells.
I consider myself a detective of the Earth. We're looking for clues in the pieces to put together the puzzle of what happened in the past.
Andrea can analyze the chemistry of the shells to reveal Earth's past climate.
You can see growth bands that show every year in the life of this clamshell.
Like tree rings, these layers reflect how clams build their shells. Encoded in each layer is chemical information about the temperature of the water. As shells grow, they incorporate oxygen from the seawater. Oxygen comes in different forms. One is oxygen-16. It has 8 protons and 8 neutrons in its nucleus. Another form, oxygen-18, has 2 extra neutrons. The colder the water, the more oxygen-18 is incorporated in the shell. This difference allows Andrea to determine the temperature when it formed.
I could take a clamshell that is 50 million years old and tell you how warm it was in the summer and how cold it was in the winter within a single year.
Each shell provides a brief snapshot of Earth's climate. But to build the full picture of past temperatures requires digging up millions of other, even more plentiful shells at the bottom of the sea, where they have accumulated over time. Research vessels drill deep into the sea floor and pull up cores of this sediment, which are then carefully archived in vast libraries of mud.
The floor of the ocean is essentially a tape recorder because there are organisms that grow either in the surface water and fall down into the sediment or on the bottom of the ocean. And we can take those fossil shells, measure their chemistry, and reconstruct what the temperature of that ancient seawater was so long ago.
Back in Andrea's lab, she sifts through the ancient mud, searching for these tiny fossil shells.
You spend hours and hours and hours picking out these tiny little shells so that we can analyze the chemistry of those shells to understand the temperature in the past.
From this ocean mud emerges a record of temperature that goes back tens of millions of years.
You can take different cores from different places all over the ocean and synthesize them in one grand record.
That record shows temperature swings from warm periods to ice ages, triggered by changes in Earth's orbit. But when these temperature changes are paired with levels of carbon dioxide from ice cores, a startling correlation emerges. The two graphs are a near-perfect match.
When we look at the relationship between temperature and carbon dioxide, they change essentially at the same time.
As CO2 goes down, so does the temperature. As the carbon dioxide ramps up, the temperature ramps up again.
Other lines of evidence confirm this correlation between temperature and carbon dioxide. When dinosaurs ruled the Earth, it was much hotter than today, and levels of carbon dioxide were higher too.
Carbon dioxide is a major driver of climate.
Just as Tyndall's discovery predicted, a key factor in regulating Earth's thermostat is the level of atmospheric carbon dioxide. As carbon dioxide goes up, so does temperature, resulting in a warmer climate. And the level measured today is higher than it has been in at least 800,000 years, and rising fast. So what is causing this increase? Earth's orbit can trigger the increase in temperature and carbon dioxide, but is not in the right phase to do so. There are other natural sources that pump carbon into the air, like volcanoes, the decay of forests, or huge fires. And there is the carbon that we have been pumping into the air since the Industrial Revolution, through the burning of fossil fuels. Which of these is the culprit for today's rising carbon dioxide levels? And how can we tell? Back in Hawaii, Ralph Keeling is working to figure that out by collecting and analyzing samples of air.
Air may not look like anything, but it's rich with different molecules. There's just an enormous amount of information content in one sample of air if you can take it all apart.
Ralph collects air in vacuum-sealed chambers, releasing the valve to pull in a sample. Just as ancient seashells have different types of oxygen, air contains carbon atoms with different numbers of neutrons. By analyzing the ratio of those different carbon atoms, Ralph can determine if the source of the carbon is ancient or not. Carbon released from burning coal or oil, made from deposits buried for millions of years, is ancient.
Fossil fuels have been locked up underground for millions of years. So when we emit fossil fuels into the atmosphere, we're emitting carbon that's very different. It has a very distinct fingerprint.
This chemical fingerprint and many other lines of evidence leave no doubt that we are responsible for the skyrocketing levels of carbon dioxide.
It is a slam dunk. We know, without question, that humans are responsible for the big increases in heat-trapping gases in the atmosphere. And that's not just theory, that's not projection, it's observations.
But ultimately, the question is, how much will these changes really impact our Earth?
When Dave Keeling started measuring atmospheric CO2 in the late 50s, the idea that humans were profoundly affecting the entire atmosphere in a way that was significant for the Earth's climate was almost unthinkable. I still think even today some people resist the idea on the grounds that, how could humans actually change something as enormous as the Earth?
One of those doubters, by his own admission, was weatherman Paul Douglas in Minnesota.
Like politics, all weather is local. We live in our bubbles, We wake up, we look outside the window, and we take note of the weather. Look at this sprawling shield of cloud cover. And it's hard to broaden your view. Even for meteorologists, we tend to be fixated on one location.
But for Paul, unusual storms and flooding in the Midwest signaled to him that climate change was real.
The worst flooding that this area has ever seen.
The devastation is massive.
And it was affecting everyone, everywhere.
Severe flooding has been reported across many northwestern parts of the country.
Lucifer is living up to its name.
The more I looked around, the more I realized that it was nationwide, it was worldwide.
Les rues du centre-ville inondées, plus de 3000 personnes.
This isn't a 30-year down the road thing. It's right now. It's happening.
What Paul came to realize was how these global changes in the atmosphere could be affecting his local weather patterns.
Climate and weather are flip sides of the same coin. You impact climate, it's going to impact weather.
Weather is what is happening in the atmosphere at a given time and place. Hot, cold, rain, or snow. Climate is an average of that weather over longer periods.
Climate is the History Channel. Weather is CNN headline news. It's a snapshot.
Paul says the connection between climate change and our local weather comes down to how much heat is in Earth's system. Always the weatherman, he takes to the green screen to explain.
Uneven heating by the sun of the Earth is what drives the weather machine. Intense direct sunlight over the equator, just a glancing blow of sunlight over the northern latitudes. Obviously much hotter here. Cold air wants to flow south, hot air wants to flow north, but there's a twist. And that twist is triggered by the Earth spinning on its axis. The combination of heating plus the spin of the Earth on its axis creates the complicated air circulations that drive our weather.
It is fundamentally these two factors, Earth's spin and heat differences between the poles and the equator, that create the weather patterns we know. So if you trap more heat in the system, you change the weather.
You put more heat into the system, there are going to be consequences, like more extremes worldwide. Weather that would have formed anyway is now supersized.
There are certain conditions that may be enhancing larger storms. We can expect more intense hurricanes going forward as our climate system warms.
We're poking at the climate system with a long, sharp, carbon-tipped spear, and then acting surprised, shocked, indignant when the weather bites back. And the weather will be biting back with greater ferocity, with greater frequency. For Predictix, I'm meteorologist Paul Douglas.
As a meteorologist, Paul has made a career out of predicting the weather for the next few days. What we need now are predictions about how our climate is changing over the next 50 years, or even hundreds of years.
We are more powerful than nature in the push we are putting on climate. And we don't entirely understand and cannot perfectly predict all of the consequences.
It's not we're worried because it's never happened before. Earth's climate has changed. What hasn't happened before is to change it this quickly.
We are so far outside the range of natural variability, we have not seen carbon dioxide levels like this in the history of human civilization on this planet.
We're really doing an experiment on the planet that hasn't been done for about 40 million years.
Across the globe, scientists are now racing to understand and model Earth's climate system, trying to figure out just how damaging climate change will be.
Red is bad.
From the ice sheets of Greenland to the deserts of Australia, and from Hawaii's volcanic peaks to the depths of the ocean. They are searching for clues in the land, sea, ice, and air, the key elements of Earth's climate machine.
Our planet did not come with a manual of how it all works. And so much of science is trying to kind of take the planet apart and understand how all of these pieces work together.
The evidence is clear that by burning fossil fuels, we humans have changed the composition of the atmosphere, which is now trapping more heat. How the other parts of the climate machine will respond will determine how much our climate will change, and how much the great diversity of life that it supports will be affected. The stakes could not be higher.
The planet has been here for 4.5 billion years, and it's still going to be here, but it will be a very different place. What I'm really concerned about is how humans will survive and how our lifestyles will be affected by this in the future.
We are already feeling the effects of climate change. We don't have the luxury of being a gentlemanly scientist in the 1850s. We have to make a difference right now.
Can we figure out the climate crisis before it's too late?
It's a planetary crisis. And it's a crisis that we've collectively created together. But we're clever enough to think our way out of this.
Flight instruments are set for departure, and we'll just follow this baby out. TCAS tested on, CVR not on board. They're set.
The efforts to think our way out of this and understand what the future may hold are now underway.
Johnny and Jim, instrument screen is stable, pneumatic panel set, ground power zeros, flap zero confirmed.
High above the Sierra Nevada mountains of California, Greg Asner of the Carnegie Institution at Stanford University is on a mission to find out what part the land plays in Earth's climate machine.
Forests are a big part of the Earth machine. To think about the world without forests would be like taking a piece of the machine out, and then the whole machine won't actually work.
These forests are home to the magnificent sequoia trees.
We're currently right in this zone, and these are the great forests of the Sierras. This is where the bulk of the giant sequoia trees live.
Greg's plane is a flying laboratory. From 10,000 feet, he uses lasers to reconstruct the entire forest in 3D, capturing 1.5 million trees an hour.
Looking good back there? It
Data's looking good. Yeah, super clean data. The technology is a huge leap forward. It's game-changing. You can't really see what the trees are doing with the naked eye, but the instrumentation lets us peel away the foliage and see the chemicals in the foliage.
Greg's measurements provide a clue to one of the surprising mysteries of climate change. Why aren't things actually worse?
We knew from Dave Keeling's measurements that the carbon dioxide concentration in the atmosphere was rising. We knew roughly how much coal and oil and gas we had burned, and there was a certain amount of carbon dioxide that wasn't showing up in the atmosphere. Now, the question is, where did it go?
We can calculate how much carbon dioxide we are putting into the air. And we can measure how much carbon dioxide is in the air. But intriguingly, those numbers do not add up.
The increase in the atmosphere is only about 50% of what we're actually putting into the atmosphere. So half of what we emit isn't even staying there, it's going somewhere else.
Given how much we're emitting, levels of carbon dioxide should be much higher than they are. So where has all the carbon gone? Finding the answer is essential to predicting our climate future.
Oh, is that speeder there? Yeah.
With his sensors, Greg is able to detect some of the missing carbon.
Okay, let's focus here for a while, and yeah, keep that on top.
His instruments can peel back the canopy of the forest below to reveal the chemical makeup of each individual tree. In this image, the red shows areas of high carbon, the blue, low carbon.
Forests soak up carbon dioxide, and they put it into wood, leaves, roots, you know, the basic building blocks of a tree. And that carbon is held in that tree.
Although trees breathe in carbon dioxide in the spring and exhale it in the fall, overall, as they grow, they store some of that carbon. This helps cool the atmosphere by reducing heat-trapping gases. All around the world, Greg is precisely recording the carbon content of millions of trees. From this kind of research, the impact of forests has become clear. They are helping us a lot.
Trees are soaking up about a quarter of the carbon dioxide that we're putting into the atmosphere per year. And so without that subsidy, without that service, we'd actually be in a more precarious predicament, making our atmosphere even hotter.
The land, part of Earth's climate machine, is playing an essential role because trees are absorbing about 25% of the extra carbon dioxide that is heating our atmosphere. It turns out that the oceans are doing the same.
Of every 2 molecules of CO2 that we put into the atmosphere, one of them gets absorbed by the surface of the planet. Half of it by the oceans, and half of it by land. Without these, the problem would be worse than twice as bad as it is already.
And there is another way that the oceans are helping us. They are absorbing heat from the atmosphere.
When we talk about warming of the climate system, we tend to focus on the atmosphere, but the lion's share of the warming in our climate system is in the ocean.
Viewed from space, Earth has been described as a blue marble. Our planet is a water world. And it is largely uncharted territory.
The oceans really are our final frontier. It's 70% of our planet. So we have to understand what's going on there.
There is no better place to understand just how the oceans dominate our climate than here in the Southern Ocean. the massive body of water encircling Antarctica. But getting that understanding can be treacherous. The Southern Ocean is as mysterious and inhospitable as any place on Earth.
The whole ocean is a mystery, but the Southern Ocean has been the ultimate mystery.
Stephen Reiser of the University of Washington is on board the research vessel Nathaniel B. Palmer. Stephen is one of the leaders of a multi-year international effort to investigate how our oceans are changing. He is now zeroing in on the Southern Ocean.
It's a very difficult place to work. Even in good conditions, the weather is terrible. In the winter, it's ice covered. So we largely have no idea of what goes on under the ice. Nobody in their right mind goes there in the winter.
Along with teams from around the world, he is building fleets of underwater drones called Argo floats to do the work. These robots are pioneering explorers, designed to probe parts of the Earth never seen before.
Deck, this is Bridge, go ahead.
Hey, just checking in.
We're right about 100 meters right now.
In the Southern Ocean, Stephen launches one of these underwater floats. And then it's on its own, hopefully for years to come.
The float is launched at the sea surface. It will signal to the satellite that it's okay. It will drop to a depth of 3,000 feet, drift for 10 days, then drop to 6,000 feet briefly, and then as it ascends back to the sea surface, it will collect data all the way up with all of its sensors on.
These sensors take the vital signs of the ocean, including its chemistry and temperature. Once at the surface, the floats beam that data to a satellite before diving back down and repeating the cycle.
You never know what you're going to get, but every observation is a gem in its own right because there aren't very many of them yet.
We've been blind about the oceans. It's just been a dark room. And the Argo floats are like flipping on the lights. For the first time, you can actually see what's going on.
So far, over 3,000 floats have been launched all around the globe. They now pepper our oceans, dutifully collecting data on an unprecedented scale.
We suddenly have a three-dimensional measurement of the ocean that's essentially continuous in time over the last 10 years. In one summer, we collected more data than we had in 50 years previously of all of oceanographic measurements.
With this information, the Argo floats have transformed our understanding of the ocean. The water in the ocean circulates. At the surface, it is warmer. But in the deep ocean, the water is very cold and has not been exposed to the atmosphere for hundreds of years. It is in the Southern Ocean that this deep, cold water rises to the surface.
The Southern Ocean is this gateway between the deep ocean and the atmosphere. There's not many places in the global ocean where that deep water can contact the atmosphere.
Once at the surface, the deep, cold water that scientists call old water soaks up heat like a sponge.
That older water has not been in contact with the atmosphere for a long time, since before the industrial era. And so this is water that hasn't seen any of the heat that has been accumulating in the climate system. When that water does come up to the surface, it's able to take up that excess heat.
The Argo floats reveal that over the last 30 years, the ocean has heated up by an average of 0.5 degree Fahrenheit. This may not sound like a lot, but the impact is enormous.
When the oceans change in temperature by a little bit, that is storing the same amount of heat that the atmosphere would store by changing in temperature by a lot.
If we put all of that heat into the lower atmosphere, the atmosphere would heat up by about 20 degrees Fahrenheit. That's how much heat we're talking about here.
We have already warmed the atmosphere 1.5 degrees Fahrenheit. Without the help of the ocean, it could be much hotter. In all, a staggering 93% of the heat that we're putting into our atmosphere is getting soaked up by our oceans. This comes with consequences. Heating the ocean and adding carbon dioxide are damaging to life in the sea. As you change one component of the climate machine, you affect the others, which can have benefits, but can also lead to devastating consequences. And one of the most urgent questions of all is what will happen when the warmer air and ocean come into contact with the polar ice caps? In a helicopter over Greenland, David Holland of New York University wants to find out how warmer temperatures are affecting this actively shrinking glacier. Today's mission is to place motion trackers directly on the ice.
We're going to go to 3 locations on the glacier and see if we can begin to understand how large glaciers disintegrate.
Constantly moving, this glacier is filled with crevasses, which makes it extremely dangerous. So David has brought along Brian Rougie, an experienced mountaineer.
It's dangerous in terms of the helicopter being able to land, and dangerous certainly in terms of being able to walk around.
They reach the first location David has picked, but there is no way to land. After 20 minutes, they find a spot that could work.
Let's give it a shot.
But the ice here may collapse under the weight of the helicopter. They must do what is known as a tow-in.
A tow-in is where the helicopter will come in and set its skids down on the ice, but not power down, so the ice doesn't get its full weight. Just kind of touches down just enough to give me an opportunity to hop out, get the gear out, and then he's able to take off again.
Without landing, the pilot drops off Brian and lifts off. This is the Jakobshavn Glacier. Ice as far as the eye can see.
It's difficult to really put into words what it feels like to look around and know that miles of ice are surrounding you. And then you have in the back of your mind, the only way out of there is that helicopter. You're certainly not walking out.
On the western coast of Greenland, the Jakobshavn Glacier is one of the fastest disintegrating glaciers in the world. The glacier meets the sea here, where icebergs break off in a process called calving. In 2015, an iceberg twice the size of the Empire State Building breaks off and floats out to sea. Speeding up a year of images reveals the glacier advancing as ice flows from inland. But from space, satellites show the glacier is actually retreating. In 1 decade, it lost 10 miles.
The Jakobshavn ice stream is pretty much the fastest glacier in the world, and it drains huge amounts of ice from the Greenland ice sheet.
And the draining of ice from Greenland appears to be accelerating.
It's almost like uncorking a bottle of wine, right? There's all this pressure of ice wanting to flow to the sea. And as you remove that resistance in the front, that ice will accelerate.
Back on the glacier, Brian has been working quickly to install instruments that can reveal how the ice is moving behind the calving wall. Brian signals to the helicopter, and they swoop in to pick him up. It's a successful deployment. The data from the motion trackers and other high-tech devices like this radar are giving Holland new insights into how glaciers disappear. What he has found is surprising. For glaciers in contact with the ocean, warmer air causes some of the loss of ice. But the real trigger for intense calving is warmer water coming underneath the glacier and destabilizing it. And David says that changing winds and currents are bringing that warmer water up from the Gulf Stream, increasing the loss of ice.
People have begun to understand that half the ice loss occurs through calving, through fracturing of ice.
This calving is a concern because ice melts slowly, but it fractures in an instant.
The fracture and breakup of the glacier could actually dominate everything. If that's the case, then the retreat of glaciers could be much faster than previously thought.
And the reason we care is there's about 23 feet of sea level equivalent locked up in the Greenland ice sheet. If it were all to disappear, oceans would go up 23 feet. Well, that's not going to happen, but, well, in the near future. But it is shrinking. It is losing ice to the oceans, and oceans are rising as a result.
The same loss of ice is unfolding on the other side of the planet, only on a much bigger scale. Locked up in the Antarctic ice sheet is a total of 200 feet of possible sea level rise. And this vast continent of ice, especially the western part, is breaking up faster than anyone thought possible.
There is a huge amount of water locked up in the Antarctic. The only question under warming is how rapidly that ice could melt or slide into the ocean.
The melting or breakup of all that ice would devastate much of civilization as we know it, as sea levels rise and flood cities and coasts. So how much sea rise can we expect from today's increasing temperatures? And how quickly? The answer lies half a world away, in a remote corner of the Western Australian outback. Andrea Dutton of the University of Florida has traveled here to work out how high sea levels could rise in the future by looking into the past.
Earth has done experiments for us in the past. It hasn't warmed up perhaps as quickly as we've seen over the last century, but it has been this warm before. Okay, fire up.
By drilling deep into this rock, Andrea can travel back to that time when Earth was as warm as today.
Every time someone takes the drill for the first time, they look at me and they say, that was really hard. I say, well, it is rock. So it takes a long time to collect a little bit of core, but it's worth it because it gives us a really important window into the past.
Oh, there we go. Now we're not mucking around.
Inside the cores, she finds fossils of ancient coral. There is only one way to explain what that coral is doing here. This whole landscape was once underwater. An ancient coral reef extends more than a mile in from today's coastline. At one location, Andrea finds some of these ancient fossils exposed and rising above today's waterline.
It looks like concrete, but you can see little pieces of corals poking up.
Corals only grow in the ocean. So wherever there are fossilized corals, there must have been seawater.
The corals that we are looking at need sunlight to survive, so they live very close to the sea surface. We use that to our advantage to understand where that sea surface was in the past by looking at how high the coral is.
By mapping this ancient Australian reef, Andrea is able to tell how high sea levels were the last time Earth was as warm as today.
You can see the waves breaking on the shoreline below me. Where I'm standing, I'm already more than 9 feet higher than that. We know the seas must have risen at least to that level to keep these corals alive.
Andrea has found similar coral formations around the world from this time period that point to even greater sea level rise.
Our research shows that just from the amount of warming we've seen today, that the seas could rise much higher, up to 20 to 30 feet higher than today.
This enormous increase is due in part because warmer water has a greater volume. But it also means that at that time, some of the world's great ice sheets must have collapsed. Today, sea levels that high would devastate cities and communities around the globe. About a third of the world's population lives within 60 miles of the coast. What's not clear is how long that process will take.
The big question is how fast. Does it take us 500 years to get there? Well, that's one thing. Or does it take us 100 years to get there? That's 3 feet in a decade. That's a lot.
In Antarctica, we see massive glaciers breaking off, adding to the amount that sea level is rising. 2/3 of the world's biggest cities are within just a few feet of sea level. And you can't pick up a city and move it.
So when will we start to feel the impact of sea level rise? Some people already are. The Marshall Islands are a nation of low-lying islands in the Pacific. They are home to 50,000 people and a vibrant culture. Today, they face becoming a new kind of refugee, a climate refugee.
We're only like 2 meters above sea level. So every time that there's a high tide, all this water gushes over and crashes into our homes and washes away graves. You feel really small. These floodings are gonna continue to the point where we can't live there anymore.
Kathy Jetnil-Kijner is a poet from the Marshall Islands. For her family, it is their homes and their very way of life that is at stake.
What's gonna happen to our culture, our traditions? We're hoping to not become nomads. We're hoping to not become lost. There's songs and chants that you can't hear anywhere else. What will happen to those stories that have survived for thousands of years? There's just things that you can't find anywhere else on Earth that you can only find in the Marshalls.
From the Marshall Islands, please welcome Kathy Jetnil-Kijner.
Kathy has become the voice of the Marshalls, addressing the United Nations with a poem to her daughter about the world she will face.
Dear Mater Filipinum, I want to tell you about that lagoon. That lazy, lounging lagoon, lounging against the sunrise. Men say that one day, that lagoon will devour you. They say it will gnaw at the shoreline, chew at the roots of your breadfruit trees, gulp down rows of seawalls, and crunch through your island's shattered bones.
Her words are an attempt to bring the realities of climate change to people who believe it will not affect them.
With only a passport to call home.
It's kind of hard to connect to an issue that you don't see outside of your own front door, you know. I understand that. It doesn't stop it from being a reality, though. If our island goes down, who do you think will be next? It's gonna be the rest of the world. It's just gonna start with us.
The results of climate change are, in fact, already striking the rest of the world, and much closer to home.
For those people who don't believe that sea level rise is happening, all you've got to do is come to Norfolk or Charleston or Miami or New Orleans or San Diego, because you can see evidence of this in every one of those cities. This walkway that was once supposed to allow people to walk and enjoy the water is now underwater.
Sea level rise is now a reality, even in the United States. And low-lying cities like Norfolk, Virginia, are on the front line. Today is a king tide, one of the year's highest, and an omen of what is to come.
It floods all the time, so like when that happens, we'll like take our furniture and like stack it up. It's been much higher than this before. It's sort of annoying to have all this flooding all the time.
The flooding may be annoying today, but it will become a tragedy if it continues. Norfolk is an important commercial port and home to America's largest naval base.
You have Naval Station Norfolk, the largest naval station in the world. Our national defense is certainly impacted by what's happening in the community outside.
Sea levels here have risen about 18 inches since World War I. About half of that related to climate change. For this strategically important port, the rising water is literally getting in the way.
Folks live and reside in the communities right outside of the base. And on a daily basis, they must get to the base to perform the duties that are vital to our national security.
Sea level rise means there's just that much more flooding, and that means that there's just that more impact to roads, logistics infrastructure, moving cargo back and forth. And so that just makes it that much harder for you to prepare that ship to go, and for the crew to prepare themselves to go.
According to retired Admiral Ann Phillips, climate change is a national security issue.
It's about readiness. The Navy does see climate as an impact to its readiness and its ability to be resilient. From a national security perspective, sea level rise is a threat multiplier or a threat magnifier.
But to the people who live here, coastal flooding has an enormous personal cost.
This house is flooded 3 times. I just don't know. I don't know how we'd be able to sell the house, honestly. I really don't.
Donna Woodward and Jim Schultz doubted they could sell their house, and so decided to raise it up.
It came down to deciding whether we wanted to go ahead and move out of the area or put all the money into elevating the house and staying.
It's happening now, not in the future. Today it's happening as we stand here. So anyone who doubts it, we invite them to buy all of this property here and to come live and see for themselves.
Sea level rise affects me in ways I had not thought of. You know, I need to be able to get to work. I bought a truck that has a snorkel.
Sea level rise affects everyone here personally, and that is going to continue to accelerate. We have no time to waste. The situation is urgent.
For the people of Norfolk, climate change is already affecting their lives. And across all of America, the costs are mounting. On a single day in 2017, a satellite recorded 3 megastorms bearing down on the Americas. Meteorologist Paul Douglas's weather team has never seen anything like it.
Look at that. It's terrifying.
This is easily going to be a $300 billion year for hurricanes.
2017 was the costliest hurricane season on record. Harvey alone caused catastrophic flooding in southeastern Texas, with financial damages that rival Katrina. And Puerto Rico was devastated by Hurricane Maria.
Warmer oceans don't trigger hurricanes, but the hurricanes that do spin up naturally have a greater potential to become extreme.
You can think of warm ocean water as the fuel supply for these big heat engines in these hurricanes. In a warmer climate system, hurricanes will have more octane gasoline to draw from in the ocean, and that drives these large, powerful storms.
Wildfires in the western United States have quadrupled since the 1980s, exacerbated by drought.
We're seeing wildfires burning greater and greater areas the hotter and drier it gets.
Effects like these are being felt across the planet, and some are even accelerating the warming itself.
See that? Yeah, red is bad.
When trees that have been helping by pulling carbon dioxide out of the atmosphere burn down, much of that carbon is pumped back into the air.
Big climate events have had massive implications for how much carbon is not just stored, but released back to the atmosphere.
And in the Arctic, ice that has been cooling the planet by reflecting away some of the sun's heat is melting. The loss of ice means more warming.
It's a self-compounding effect. As temperatures warm and ice starts to melt, the ice and the ocean system absorb more energy, which causes the temperatures to warm more, which causes more ice to melt, and so on. Once it begins, it wants to run away in big ways that will further accelerate climate change.
We're so completely vulnerable to our climate. We're just incredibly vulnerable to changes in our climate, especially rapid changes.
As virtually all peer-reviewed scientific research confirms, the case for climate change caused by human activity is overwhelmingly clear.
It's real, it's us, the risks are serious, and the window of time to prevent widespread dangerous impacts is closing fast.
A lot of times people ask me, doesn't your work terrify you? And yeah, it does. It keeps me awake at night sometimes, thinking about my children or what will become of my state or my country or my relatives in the future. It is a scary thought. But what gives me hope is that we understand this. And we have an incredibly good idea of what is about to happen. So we actually can do something about it.
To do something about our climate future, we need to know what lies ahead.
It's kind of as if you're driving down one of our dead straight roads here in Texas. You can be driving down the road, even staying in your own lane, if you're driving along looking in the rearview mirror, because the road is completely straight. So where you were in the past is a perfect predictor of where you're going to be in the future. But what if you're driving down this road, looking in your rearview mirror, and a giant curve comes up? You're going to run off the road, because the past is not a perfect predictor of the future if the road is changing.
To see the road ahead, scientists at the Geophysical Fluid Dynamics Laboratory in Princeton, New Jersey, are working to turn our understanding of how the land, sea, ice, and air interact into a powerful simulation called a climate model.
Using nothing but basic physics, we can actually produce in our computers a virtual Earth.
With this virtual Earth, scientists like Kirsten Findell work to predict where our climate is going before it's too late to change course. The first step is breaking the climate machine into its core components.
Every climate model has 4 major physical components represented. We represent the ocean, we represent the land, the sea ice, and the atmosphere all around the Earth. Within those 4 components, we also then break up the Earth into little grid boxes. And then we can slice up the atmosphere into thin layers and slice down into the ocean to thin layers in the ocean and down into the soil.
Once they have divided the system into manageable parts, they use well-established mathematical equations, grid box by grid box, to run the model forward in time.
These models are amazing. They can produce weather systems, even hurricanes. They can produce droughts and floods.
Worldwide, there are dozens of models. They predict how each part of the climate machine will change, like sea surface temperature, storm intensity, or the extent of the ice caps. Every detail is included. But the path to perfect models is still a work in progress, because Earth's climate machine is such a complicated one. The role that clouds play, for instance, is important, but poorly understood. And the speed at which ice sheets will break apart is another big unknown.
We're definitely making progress on making better predictions, but there is still an enormous amount about the climate system that we don't fully understand.
But the models can be checked against things we know, like air temperature over the past 100 years. The models can be started in the past and run forward. The blue line shows the average of those predictions. When compared with the actual temperature record, in red, their accuracy is revealed.
Computer models don't exist in isolation. We calibrate them against what we've observed. We test them against the history of climate change, and we now know they're pretty good.
The models can be used to run a virtual experiment. If we continue emitting carbon dioxide on the path we are on, what do they say our world will look like in 2100? This map shows how temperatures could change. The models predict the average temperature could be 5 to 10 degrees Fahrenheit hotter. That means in New York City, days with temperatures over 90 degrees would more than triple. And in the Arctic, which will heat up even faster, it could rise on average more than 15 degrees.
One of the things we understand really well about our climate system is that if you crank up the average temperature of the planet, it is going to fundamentally change your weather.
Their results suggest we will see more Category 4 and 5 hurricanes, and the prevalence of devastating heat waves will be much more extreme.
The models also show that by the end of the century, it is likely the ocean will rise 1.5 to 4 feet. Without major changes, this would put parts of cities like Miami underwater. And new insights are coming in all the time. The work of David Holland and other scientists suggests that if large parts of western Antarctica break off, 8 feet or more of sea level rise by 2100 is not out of the question.
All bets are off for Antarctica. That is a place where very large sea level rise on the scale of 100 years is quite possible. That doesn't mean it will happen, but it actually could physically happen.
The road ahead is a world that could be increasingly hard to live in. The question now is, what can we do about it to reduce the possible damage?
We're going to figure this out because in the end, we are not going to have a choice. We're going to have to figure this out.
The path ahead comes down to three basic options. We can do nothing and suffer the consequences. We can adapt as the changes unfold. Or we can act now to mitigate or limit the damage. The options are connected. The more we mitigate, the less we would need to adapt. The more we adapt and mitigate, the less we would suffer.
Society has only three options. And if we want to minimize suffering, as should be our goal, we need to maximize both mitigation and adaptation.
Adaptation is perhaps most urgent in the ocean, which right now is bearing the brunt of climate change by absorbing most of the heat. Billions of people depend on the sea for food or their livelihood. As temperatures rise, many species of marine life are moving to cooler waters, threatening local fisheries. And warmer water is killing off coral reefs, which support about 25% of all life in the sea. This photo was taken in Florida in 1975. This is the same reef now.
We have lost 50% of the world's reefs in the last 30 to 40 years. That's, even when I say it, I have to be honest, I still find it shocking and I want to find a reason for that figure to be wrong. But it's not wrong. The majority of the world's reefs will be dead by 2050.
Ruth Gates runs the coral lab at the Hawaii Institute of Marine Biology and is working to save the reefs by helping them adapt.
If there's any bleached corals that we see, we want to get those tagged. Sounds good.
Today, her team is out monitoring the health of a reef in Kaneohe Bay. Coral reefs may be a case study in the devastating effects of climate change, but they also offer a lesson in survival.
If 50% of the reef has died, let's just turn that around and talk about the fact that actually 50% of the reef has survived. Our question's why?
To help answer that question, the team prepares a sample of coral, puts it in water, and places it in a cutting-edge microscope that can view living coral in real time. Under ultraviolet light, we can see the coral filled with algae, or tiny plant cells, that give it a red color. They are essential for the coral's survival because they provide nutrients the coral needs.
Where you see the bright red, that bright red is the pigment deep inside of the tiny plant cells. They power the system.
Ruth can turn up the heat of the water and watch what happens. The coral belches out the plant cells in tissue that looks like a black cloud, turning the living coral from a vibrant red to a lifeless, empty black. But not every coral reacts to heat in the same way. Ruth and her team work to identify and grow hardy coral that can better withstand the heat.
If we had a lot of time, this is exactly what nature would do. Essentially, it kills off the ones that can't survive the new conditions, and then it selects for the best of the best.
She calls these winners supercorals and hopes to use them to repopulate reefs around the world. There is no time to waste.
It's mind-blowing to think about it. species who've been on the planet for, over 200 million years wiped out in less than 50.
Gates says that if coral is to survive, it must adapt, and fast. And ultimately, so must we. Adapting to our changed climate is already in the works in places like Norfolk, Virginia, where streets are regularly flooding.
What are we going to do to make sure that we can adapt? What are we going to do to bounce back and evolve?
What actually changes from what we see now?
Colonel Jason Kelly of the U.S. Army Corps of Engineers is overseeing a plan to cope with the rising water.
The city has to change. Norfolk is reimagining itself in a way that will permit resilience.
The Army Corps of Engineers has proposed spending more than $1.5 billion on an adaptation plan for Norfolk to keep it operating for the next 50 years. The plan includes a 5-mile flood wall, water-retaining parks, and surge barriers. But adaptation can only go so far. Houses are still at risk. And managing a few feet of sea level rise is a lot different than the worst-case scenario of 8 feet by 2100.
Keeping all of that water in the river will be a challenge. It can be done, but it's going to be a very different city if it's 8 feet.
Across America, cities are drawing up plans to adapt to the impacts of climate change. Whether that's too much water from rising sea levels and stronger storms, or too little water from harsher, longer droughts.
You start to talk about different ideas when you realize that we have a big problem on our hands and we have to consider now how to fix it.
But there is a way to avoid the worst impacts of climate change in the first place. The more we mitigate or limit how much our climate changes, the less we will have to adapt. That will require shifting our economies away from burning fossil fuels. The good news is technology is moving so fast, there are many alternatives.
The scientific toolkit finally got big enough to crack this thing. Wind and solar are much further ahead than anybody ever thought they would be 10 years ago. They're growing impossibly rapidly.
The proof of that rapid transition can be seen in Findlay, Ohio, middle American, blue collar, and home to a Whirlpool factory spinning out dishwashers.
This is Whirlpool's Findlay operations. We have roughly 2,700 employees that work here, and we make over 15,000 dishwashers a day.
At this factory, cheap power is essential to the bottom line.
We are constantly looking how we perform better day in and day out. We looked at our energy costs rising. The question was, can we reduce the cost of the energy that we consume?
To get the energy this factory needs, Whirlpool decided to add a twist to their production line of dishwashers. Wind power.
There's enough wind energy, if you could capture it, to lighten the world. The question is, how much of it can you capture?
Whirlpool turned to Jeremy Kent, a 32-year-old CEO of a company that is taking on the big utilities by harnessing wind power right at the factory door.
Our wind turbines directly power the customers they serve. We take utility-scale wind turbines and we install them for the biggest power users around.
In terms of how we operate here, you would not know that 15% of our power is generated by wind energy.
Nothing has noticeably changed at this factory, apart from long-term energy savings. Wind is such good business for Whirlpool, they ordered 7 more turbines for other plants in Ohio.
We aren't doing this because it's good for the environment. We're doing this because it's good business. It happens to be good for the environment, it happens to be great for the environment. But that's secondary to the fact that it has to have a real business need if you want to run a business around it.
Wind technician is one of the fastest growing professions in America. And for Jeremy, a dream job.
I got into this business because this was the coolest thing I could find. You're telling me I get to go out and play with cranes that weigh 1 million pounds and build a 400-foot tall structure? Okay, where do I sign up?
These turbines are over 40 stories high, with rotors the size of a football field. Each can produce enough electricity to power up to 400 homes, or make a lot of dishwashers.
It's time to innovate and it's time to change. Instead of having one plant that makes 1,000 megawatts, let's have 100 plants that make 10 megawatts, or 1,000 plants that make 1 megawatt.
We're going to want to run the production model.
Kent has developed an innovative approach to a tried and tested technology: wind. Others are developing entirely new technologies. One of the best places to see that in action is at the National Renewable Energy Lab, or NREL, outside of Denver. Think of it as an invention factory for carbon-free, renewable energy.
They're working on endgame technologies that fully fill the gap between where we need to go and the track that we've been on since the beginning of the Industrial Revolution.
So where do we need to go? Jet fuel made from plants, taller, more powerful wind turbines, better batteries, and the next generation solar cell.
It's not every day that you get a chance to really work on a technology that could really change the way we live. And this is going to change the way we generate electricity. It's really exciting. Hey, Rosie.
Joseph Berry and his team are working to reinvent the solar cell.
The sun is the biggest energy source we've got access to. And if you look at how large that resource is in comparison to what we use, it dwarfs it.
The problem is that manufacturing and installing today's solar is still relatively expensive. That's where Joseph and the other scientists at NREL come in. They think they've found a game changer in a class of materials called perovskites.
We love perovskites. This is the coolest solar material, I'm going to say ever, but certainly the coolest solar material in the last 20 years. We can make it so easily. We could make an awful lot of it, we can make it really cheap, and we can make it really fast.
What perovskites can do is remarkable. Similar to the silicon that is currently used in most solar cells, they take energy from the sun and turn it into electricity. But while silicon requires exacting production techniques, perovskites are easy to work with and can even come in a bottle.
Think of it like an ink. The nice thing about working with liquid things is that you have a wide variety of ways you can apply it. We can even put it on with a paintbrush.
With just a few strokes of perovskite paint, these solar cells can generate power as efficiently as silicon.
That's what makes it completely transformational. Imagine being able to integrate it into essentially every road surface, into fabrics. We're really talking about a future where solar is integrated into everything, everything, full stop. Your house, your car, your jacket, the whole shebang.
While perovskites are still several years from hitting the marketplace, already it is cheaper to create energy from solar or wind than building new power plants that use coal or nuclear. But the wind doesn't always blow. The sun doesn't always shine. And changing our entire existing energy system is not going to happen overnight. Fossil fuels still account for 80% of the world's total power. And many people rely on them for their jobs and livelihoods. What if we could still burn fossil fuels, but without emitting carbon dioxide? That's an idea they're developing at Sask Power in Canada. One of the 4 coal-fired units here has been modified. Instead of releasing its carbon dioxide into the air, it is captured and pumped more than 2 miles underground, where it is effectively stored.
That facility takes CO2 and injects it deep under the earth. There aren't more of these right now because there's no commercial reason to do them. There's no economic incentive.
While carbon capture may be good for the environment, it's not good for business. So is there a way to make it pay?
There are many things that can be done scientifically and technically, but the question is how much does it cost and is anyone going to pay for it?
Where others see a waste product, Lisa Dyson sees potential.
When people think of carbon, they often think of fossil fuel emissions, but carbon is everywhere. We're made of carbon. We're a carbon-based life form. The carbon's in our food, our yogurt, our ice cream, our cheese sandwiches.
Lisa has started a company that uses microbes to take carbon dioxide and turn it into something we can use.
So we have carbon dioxide bubbling into these bioreactors, and we have single-celled organisms, these supercharged carbon recyclers, that are making complex molecules like proteins.
The microbes ingest carbon dioxide and help convert it into products like protein or oil for food, plastics, even cosmetics.
We do it because it's good for the planet, but we go to the companies and we show them how it will be good for their business.
Lisa envisions a day that our choices for solving the climate crisis are not just suffer, adapt, or mitigate, but also prosper. By learning to recycle carbon dioxide into useful, everyday products. If carbon capture and renewable technologies become more widespread, carbon dioxide levels will stop increasing. But even reaching that goal may not be enough, because we would still have record high levels, continuing to warm up our planet. We may need to find a way to pull more carbon dioxide out of the air than we emit into it, to go into what's called negative emissions.
We don't just have to go to 0 emissions. We've actually got to go negative. We've got to suck stuff out.
Fortunately, there is a way to do this already built into the climate machine: photosynthesis.
A very simple way to remove carbon dioxide from the air is called photosynthesis. Plants do it every day for free.
For geologist Dave Montgomery and his wife Ann Biclay, solving the climate crisis starts in their own backyard.
When we bought our house in North Seattle, the yard had really wretched soil. It wasn't what my gardener wife wanted.
The first step was improving the soil by adding extra plant material and enhancing the natural process. Plants pull carbon in from the air and turn it into sugars. They pump some of those sugars down into their roots to feed microorganisms, which use the carbon to build healthy soil. And when the plants decay, more carbon is added to the soil. But modern gardening and agriculture can disrupt this process and send the carbon back into the atmosphere. When Dave and Ann moved into their new house, the carbon content of the soil was less than 2% and looked like this. About a decade later, it's much richer and packed with carbon, almost 10%.
Those are big changes, going from 1% or 2% to pushing 10% over our whole yard. That's tons of carbon sequestered as a consequence of gardening.
And what works for this small garden could work for enormous fields.
We could do the same thing on the world's farmland and sequester an awful lot of carbon, enough to take a bite out of global fossil fuel emissions.
Come on.
That is precisely what Minnesota farmer Dave Legvold is now doing.
Good dog.
This is 40 years that we've been on this farm, and I've been farming.
When Dave started working on the farm, he found the soil was in bad shape.
It was abused for about 30 years, and I watched my soil washing downhill and leaving my farm. And I thought, this is not good.
On most farms, the soil is tilled or plowed to reduce weeds and pests. But in the process, much of the carbon gets dug up and released back to the atmosphere. Dave decided to go another route, called no-till farming.
Every time you harvest, you leave the residue from that crop in place, so there is a protective blanket on the top of the soil.
So here we have residue left from last year's corn crop. Corn stalks, leaves, an occasional corn cob.
Not tilling helped the soil become healthier.
Despite the benefits, no-till remains an unorthodox method. So Dave has a fair share of neighbors who think he's a bit crazy.
Neighbors look at a no-till field and they say, oh my goodness, how can you grow a crop in that shabby-looking field? But at the end of the season, my yields are as good or better than the fields that have been tilled.
Not only is the soil healthier, but it absorbs much more carbon. No-till, combined with other agricultural techniques, could capture more carbon dioxide than is emitted by all the cars in the U.S.
We need to fundamentally rethink how we do agriculture, focused on soil building, soil health, putting carbon back in the ground. And if we're able to do that, then agriculture could be a major contributor to very positive changes related to global climate.
In the climate machine, the land already absorbs significant carbon dioxide out of the air. The right agricultural practices could absorb even more, as would planting more trees. There are even high-tech artificial trees in development that could absorb up to 1,000 times the carbon. There are many strategies to address the climate crisis. It's likely we'll need all of them.
We need more renewables. We need to surmount the challenges that face expansion of nuclear energy. We need to do better at energy efficiency. We need to learn how to remove carbon dioxide from the combustion gases from fossil fuels. We've got a lot of work to do.
For over 200 years, in every corner of the globe, scientists have probed Earth's climate machine, developing a deep understanding of how it works. They have proven beyond reasonable doubt that climate change is happening, and that burning fossil fuels is the primary cause. They have built computer models that can predict the road ahead. And they have come up with ways to adapt, or solutions to avoid the worst of the impacts. But there is one powerful piece of the climate machine so unpredictable and inconsistent that no computer model could ever guess how it will behave. Us.
You know, there are some people who say, well, the future of climate change is too uncertain to justify action today. But in fact, the largest uncertainty about the future of climate change is what we decide to do.
In terms of how temperature is going to change, what's going to happen to our drought and our flood patterns, how much sea level is going to rise, one of the biggest uncertainties are what are the choices that we are making today.
Figuring out how to respond to the climate crisis is where science meets politics. And the issue has become highly contentious.
Up until about 2008, there was bipartisan support for climate action. But it's been turned into a political football, and that's unfortunate because Republicans' homes are going to flood just as readily as Democrats' homes.
I know we're living in a divisive era.
I know it's divisive out there politically, but the oceans are warmer. That's not a model, that's just going out and measuring the temperature.
Meteorologist Paul Douglas, a conservative, was once skeptical of climate change,
How bad was your town hit?
but now is convinced we must act.
Our text line is 81807. We want to hear your stories too.
We need to get past denial, and we need to find some common ground. We can debate policy. Let's not debate the facts.
The scientific evidence is so clear about where we're going. But there's an astonishing inertia. We're not mitigating fast enough to stop the train crash.
The technological solutions make it inevitable that we will solve this problem. The question is just how much damage we create before we finally rein it in.
We can wait. We can do nothing for 50 years, but we will have dug a much, much deeper hole for ourselves to climb out of.
The evidence for human-made climate change is solid. Solutions for how to stop or slow it are available. The greatest uncertainty is us. This is not a problem far off in the future. Nearly 2 billion children alive today, like Matafele Bainum of the Marshall Islands and Aaron Myron of Norfolk, Virginia, will live to see what happens. Depending on how we respond, they could inhabit a very different world.